Okay, and then here's one more example regarding impulse and momentum. You may have seen in class a demonstration of the happy versus the sad balls. So I have two rubber balls. Both of them are identical mass, just one of them, when it falls and hits the ground, bounces back up, not to the same height it was dropped from, because there's a little bit of wasted mechanical energy converted to thermal energy in the process of bouncing. When the sad ball is dropped and hits the desk, it hits and just basically stops in place, almost like a ball of clay would hit the desk. Okay, so what happens when I throw these balls against a wall? So let's start with the happy ball. When the happy ball is thrown against a wall, maybe I throw it to the right with a speed of, I'll use a different notation here and say motion to the right is negative and motion to the left is positive. So I can imagine throwing this ball with a speed of 10 meters per second to the right. It hits the wall, and if it is the happy ball, it's going to bounce back at nearly the same speed in the opposite direction. So it comes back the other way with a speed of 10 meters per second. What I really mean is the final velocity is positive 10 meters per second, and the initial velocity was negative 10 meters per second. So the change in velocity in this case would be final minus initial, which is positive 10 minus negative 10, which gives me a change in velocity of positive 20 meters per second. The change in momentum would be equal to whatever the mass of the ball happens to be multiplied by this change in velocity of 20. Okay, what happens when I throw the sad ball against the wall? So it's moving to the right with a velocity of negative 10 meters per second, hits the wall, and basically just falls down to the ground. So the change in velocity in this case, final minus initial, would be 0 minus negative 10, which would give me a change in velocity of positive 10. So it's half the change in velocity it was in the case of the happy ball, right? Which means it's half as much momentum. Well, if it's half as much momentum for the sad ball as the happy ball, then it must be half the impulse as well. Right? The impulse for the happy ball is going to be roughly, the impulse for the sad ball is going to be roughly half as much as the impulse for the happy ball. That means it's probably colliding less forcefully with the wall. So I have a demonstration I'd like you to watch where I roll the balls down a ramp and have them collide with a wooden block. First, I roll the sad ball down the ramp and it hits the block with some amount of force, and then I'm going to replace it with the happy ball and let it roll down. So you make a prediction. What do you think it'll look like comparatively when the sad ball rolls versus the happy ball? Okay, did you make your prediction? How about this? Press pause on this video and take a look at it. Watch the video where I roll the happy and sad ball down the ramp and see what happens. I'll give you a moment to hit pause and see what the outcome is. Okay, so were you right? Did your prediction match your observations? People who have gone paintballing might be familiar with this same demonstration. So hopefully, every time you get hit with a paintball, the paintball hits your body, goes splat, and as long as you're wearing fairly padded clothing, it doesn't hurt too much. Once in a while it'll leave a bruise, but not too bad. That's very much like the sad ball colliding with the wall. But every now and then, the paintball hits your body and doesn't break and bounces off almost the same speed. And it's much more forceful, much greater amount of force of impact in that case, right? If the object reverses direction, it's a larger change in velocity. If it's a bigger change in velocity, it's a bigger momentum. If it's a bigger momentum, it's a bigger impulse, and bigger impulse is associated with a greater amount of force. So next time you play paintball, or if you ever play paintball, watch out for those balls that don't break when they hit you.